let's review kinematics and centripetal acceleration and centripetal force and forces in motion and all that good stuff in Newtonian mechanics. So first off, we have displacement. And remember that that's different than distance or position because it's the change in position. So that means if a football player started at one end zone, went to the other end zone, and then back, their displacement would be equal to 0, but they would have gone a distance of 200 yards. So just remember that difference as we talk about displacement and velocity throughout physics. So in speaking about displacement, we should also talk about velocity. So we have instantaneous and we have average. Instantaneous just means that at any given time, a specific time, we could calculate velocity. And while this is important, this probably will not be the main type of velocity that we discuss in this class. We'll most often be talking about average velocity. So that's the final position minus the initial position divided by the final time minus the initial time. And we write that as kind of a swirly V with a bar across the top. And that bar represents average. We also have speed. And speed is kind of like velocity in that you discuss how fast you're going, but speed does not incorporate direction, whereas velocity is a vector. So that means that it has speed plus direction. And speed is just distance over time. We also have acceleration. And the equation for average acceleration is the change in velocity over the change in time. So obviously that means final velocity minus initial velocity over the final time minus the initial time. And sometimes you might see instead of initial velocity, it's the same as v naught, which means v at time 0, or the starting velocity, v naught. We also have instantaneous acceleration, so at any given time the acceleration of that particle or thing, but just like velocity, we probably won't be discussing that a whole lot. So that gets us to some kinematic equations. So here are some kinematic equations that you might see. We have V equals V naught, excuse me, there we go, plus AT. We have average velocity equals V naught plus V over 2 for given a constant acceleration. We have final position equals V naught T plus 1/2 AT squared. So if there's nothing here, you assume that it's final. And we have velocity squared, or final velocity, you could do it like that, or just nothing, equals V naught squared plus 2AX, where X is its displacement or distance or position. As I mentioned before, velocity is a vector, and you can add vectors, there are vector components. All of that is covered in chapter 3 of the book. So if you need some brushing up on vectors, then you can grab a text, take it home, read up in chapter 3. And those vector components really matter in projectile motion, circular motion. Anytime we're talking about velocity, obviously we have a vector, but those are kind of some main ones that are important. Also when we talk about forces. So we started to talk about centripetal force and centripetal acceleration the last couple days just as a way to review these concepts. So as a reminder, we have centripetal acceleration is A with a little c, and that's v squared over r. So that means that centripetal force, if we remember that F equals ma, we plug this centripetal acceleration in for that a, so we get F equals mv squared over r. And we have Newton's laws, and his first law involves inertia. And that's when you guys tell me, oh, an object in motion stays in motion, or an object at rest stays at rest unless acted on by an external force. Well, that is the definition of inertia. And we have his second law, which I actually already mentioned, is F equals ma. So that means that the acceleration of an object is directly proportional to its net force acting on it and inversely proportional to its mass. And then Newton's third law is that every action has an equal and opposite reaction. So that's where things like normal forces come into play. So if I have a box sitting on a table, it has the force of gravity, or its weight, pointing down, and the normal force is then pointing up. And just a reminder that the normal force is always acting perpendicular to the surface. So if I had an incline, which is kind of a typical physics drawing, the weight of the object would be pointing straight down, but its normal force would be perpendicular to the surface. So we would need to do vector components to figure out the different components of the normal force to get this resultant here. And we have things like friction, and there is static friction and kinetic. And kinetic just means that it's moving. So F equals ma, remember. And in that case, it depends on kinetic or static. So if we're talking about static, we have static friction force is mu sub s times the normal force. And if we have kinetic, this should be a k, equals mu sub k times the normal force. And I use a capital N, you might have used a small n before. Ultimately it's all the same, and the convention is not totally, there's no convention for that. There are also things that we'll review like pulleys and work and energy, but we'll talk about those another time.